Okay, and a good morning to everyone. And that was Jim Morrison, The Doors, Break On Through to the Other Side. Sean asked if that meant we're breaking through another month. It's the 1st of October. I think it's just trying to break on through past the material we're doing. This is the time of the semester when you realize that, at least I am, that there's a perpetual feeling of being tired. It doesn't seem to escape you in the weekend, and you just realize that that's the semester, and we aren't to the point where you can look at the end of the tunnel. So that's academia. I spent most of my life that way. So you get used to it, I think. There are several topics as a kind of follow-up that I'd like to cover this morning. They are ancillary topics, if you will. I'm going to spend time in the study guide, considerable amount of time in that. It's going to be in Chapter 4, which is probably going to be one of the most critical things to probability that you have available to you to try to put some pieces together. We've talked about a probability experiment. The idea that you have some process, something you do that results in a sort of random set of outcomes, hence a random variable. And we look at the outcomes, and if they are in terms of a finite number of outcomes, we refer to it as a discrete random variable. I've used the phrase, if you can count, it's discrete. If you have to measure something, continuous. But the idea of a continuous random variable is that you have an infinite number of possible outcomes. And so as we looked yesterday, let's see, today's Wednesday, so I think it was yesterday or Monday, it's in the last 48 hours, we looked at a triangular distribution that went from 0 to 2, had a height of 1, and we said that that was a continuous probability distribution, and I've given to you, I think, two versions of it. One is in your book with an isosceles triangle, and the other was a right triangle. And the density curve was a straight line in both cases. But we do have the continuous probability distribution, and one of the things I really didn't adequately reference to you, in the standard normal curve, Table A is in essence your probability distribution model because it gives you the probabilities for different intervals. So it's an effort to give you some areas that have been pre-calculated for you so you don't have to do the work. So if we can get a z-score, we can find the area between two z-scores using Table A rather than having to find areas under a triangle or resorting to calculus to find the area under that density curve. We introduced some vocabulary, and one of the key phrases was a set. And I keep coming back to this week, trying to, as we keep referencing some of these phrases, that they will seem a little more familiar to you. A set being a collection of elements. A set technically is undefined. We talk about what's inside a set. We call those elements. And if our set is of the outcomes of a probability experiment, we refer to that as a sample space or outcome space. Now, I referred to it originally as an outcome space because we looked at the outcomes. But it is, in our text, as is in many texts, referred to as a sample space. Events. We talked about that yesterday, and I tried to draw out of you the idea that an event was a subset. A subset of the sample space. And so we talk about the probability of an event. Now we had to contrast two things. One was the idea of equally likely. And we did that whether it was a regular die or a tetrahedral die. We looked at both of those. We said each outcome had the same chance of occurring, equally likely. And we had a nice formula for finding the probability in those cases. You looked at the number of elements in the set E, looked at the number of elements in set S, and said the ratio is your probability. But yesterday I introduced you to Benford's law, where the probabilities of getting 1 through 9 are not equally likely. Otherwise, roughly a 30% chance of getting a 1, 5% of getting a 9. And so if you want the probability of that event, then you look at the elements in the set. They are sometimes referred to as simple events. And you find the probability of getting each one of those and add up the probabilities. Now that generated a couple of formulas. The addition rule. So if I have two events, E and F, we talked about the probability of E or F, and we said that was equal to the probability of E plus the probability of F under one caveat. And what was the restriction? That A and B had to be, or E and F in this case, had to be what kind of events?
Disjoint.
Disjoint, their intersection had to be the empty set. So we did talk about union and intersection of sets, and so far we've looked at the idea of union. Instead of saying E or F, we could say E union F. So whether you look at predicate logic or set theory depends on whether you want to say E or F versus E union F. Otherwise, I can define E if I have a outcome space of a single die, and I could say E is going to be the event even numbers. And I could define F as the event multiples of 3. Now, E or F in predicate logic makes sense there. But if I give you the set E containing 2, 4, and 6, and the set F containing 3 and 6, then it makes sense to talk about E union F. So there's that duality, if you will. We also said that probabilities had to be between 0 and 1. And a question was asked this morning before we started about problem 10 on chapter 10. Would you go to 1010, please? 1010. We'll just take a moment there. This is a set of possible probability models. Now, a probability distribution I mentioned to you yesterday is like a probability function. We have a set of x, y's. And for every x, there's exactly one y. And that's exactly what we have in 1010. What page is 1010? 256. I feel like one of those television advertisements, 10, 10, 10. On 1010, you have a variety of models presented. Now, what did we say as part of these rules, if you will, that we had for probability in the last couple of days? One of the rules said the probability has to be between what two values inclusive? 0 and 1, correct? Each probability has to be between 0 and 1. We'll look at the last, I think it's model 4 on 1010. And you have a probability there too. Can't be. So that can't be a probability model. And all a probability model is, or a probability distribution, is a statement of each possible value of x and the probabilities associated with it, under two restrictions. Every probability must be between 0 and 1. Second restriction is what? The probabilities, when you add them together, must equal 1. So you could look at that fourth model and argue 2 violations, because the sum of the probabilities is certainly more than 1. Okay, in the first model, you have 1/7 for each one, correct? Now that's between 0 and 1. But when you add those 6 values, you get 6/7. And that's not equal to 1, so it can't be a probability model. You go to number 3. And I believe there that you end up with the sum of the probabilities being greater than 1. Is that correct? It's sort of like a weighted die, but I think you end up with, there's a third there that becomes 2/6, and so if you add everything up, you exceed 1. It ends up, I think the second one is the only one of those 4 that meets the criteria that you have set. Those 2 criteria are each probability between 0 and 1, and the sum of the probabilities must equal 1. Now clearly this problem was wanting you to focus on what do you need in order to have a probability distribution? And are you violating it? As we work with probability historically, there have been a couple things that you would find in most books. One is called a Venn diagram. And a Venn diagram was an effort to show you what sets look like. Now, I'm going to show you a classic Venn diagram, the way they were done for decades. It's on page 308. This is your classic Venn diagram. Now, the notation here in terms of not E. Remember we had a complement rule. Probability of E is 1 minus the probability of not E. So we talk about not in the event, and so this is what this problem or this diagram is referencing. What I want you to see is two circles. These two circles represent events. And where they overlap with that deep green, forest green, in the center is your intersection. Reminds you of a MasterCard? I hate to mess up your life, and every time you look at a MasterCard now, think of statistics. But you look at it as intersecting sets in a Venn diagram. Now, as we look at this again, the rectangle is supposed to represent the universe of all possible values you might have. And then the individual sets might be E and F, in this case, D and T. One of the fascinating things that's occurred as we have gone to modern technology and artist renderings and a textbook, now publishers feel obligated to avoid circles. And so we get kidney beans and amoeba cells or something like that. And now we have the two events, A, B, and that forest deep green in the middle is A intersect B. It's a little bit more difficult here to illustrate A union B. We would need to have everything the same shade. But this has become the more nuanced Venn diagram. You're more than welcome just to draw circles. You don't have to draw silliness like this. Now that is used to try to explain to you why some of our rules look as they do. One of the more classic ways of dealing with probability is through what is called a tree diagram. Now, yesterday I was reviewing a book we're potentially going to consider using. That's very vague, potentially consider. But for our intermediate, our pre-algebra course. And there's a thing called a factor tree that I suspect you at some point in arithmetic did. If you were trying to write the prime factors of, say, 36, so you want to write 36 as a product of primes, you break it down into two factors, a 4 and a 9, and then you break those 4 and 9 into a 2, 2, and a 3, 3, and now you have 2 times 2 times 3 times 3. Factor trees. Well, I've illustrated that for you on 4-6 of the study guide. Here's your classic factor tree. And as I say, I was looking at this yesterday just in another book. So the idea of a tree should not be unfamiliar to you. Well, that same idea is used in statistics, particularly in probability. And if we look at 4-6, we now don't call it a factor tree, we call it a tree diagram. And the argument is if you rotate this about 90 degrees counterclockwise, you have a tree without a trunk. But it sort of branches out. And this happens to be what happens when you toss a coin 2 times. So in the first toss, you have a head or a tails. And each of those then have a toss following them, which again can become head and tails. And so we draw a diagram like this to reflect what we are doing. And as we go to 4-7, we look at an embellished tree diagram in which, in this case, as you look at the monitor, I've included the probabilities that are associated with each of these outcomes. So in a coin, you have a probability of 1/2 of heads, 1/2 of tails. And in the subsequent toss, there is no memory. The coin still has a probability of 1/2 of heads, 1/2 of tails. And so you can put the probabilities associated with that. And then you can go ahead and you can actually extend this to looking at the possible outcomes, much as we would with a die or a pair of dice. And so we can list the head, 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 tails, tail, heads, and tail, tail. Now what will happen out of this, and this is not something we've talked about, I'll just say at the moment, if you want the probability of that outcome, you multiply the probabilities in the branches. So you get 1/4 here, 1/4 here, 1/4 here, and 1/4 here, and we would say the probability of head, heads, a head and a head, is going to be the product of those two individual probabilities. That is under a very restricted condition, but we call that a multiplication rule. Now, if I look at that same idea, and here's where tree diagrams are argued, that you can look at your sample space in a very organized way. Now, the next diagram for a single die is pretty easy to do in a computer. This was a part of the study guide when it was originally set in a what we call desktop publishing. That's the phrase that comes to my mind. I don't know if that's the correct genre right now. But the idea that you load everything up front. So you submit to the publisher a file in which everything's been done, and all they have to do is print that file. That's different than you send a manuscript to a publisher. They set everything up, bring in an artist, and go through that process. So everything in here is what I chose, that I wanted, the spacing that I wanted, and then I just send the finished manuscript, and they print it. Now, the tree diagram, and if you've ever done any graphics work on a computer, you maybe can appreciate a little bit more of what's going to be illustrated here. But this is the tree diagram for a single die. Now, with that diagram, I could indicate 1/6 for each of those little branches as the probability of each of those outcomes being equally likely. And the tree diagram is going to become very important to you as you list outcomes. Here is the same effort to run this tree diagram with 2 dice. Okay? This is on page 410. Well, the camera's dropping on me. Continues to slide gently. But you see the difficulty you would now have if you went to the Yahtzee problem? There's your 36 branches for 2 dice. How many branches would you have for Yahtzee? 7,776 branches. So there's a bit of insanity that can go with a tree diagram, and your text only alludes to them ever so briefly, but they're going to be very important to us this next week as we look at some results. This is a particular 3 coins in a fountain, the Trevi Fountain in Rome. And so you're tossing the coins, and the idea is that you can have 2 outcomes for the first coin, 2 outcomes for the second coin, and 2 outcomes for your third. So that's 2 to the third outcomes. Here are your 8 branches. So you have the head, head, heads. I'm on page 411, finishing out with tail, tail, tail. And again, the probabilities are simply the product as you come across each of these outcomes equally likely at 1/8 for probability. Now you're going to have problems where you might draw cards out of a deck of cards. Your standard deck that's used in things like poker. And again, please understand, we're going to talk about gambling a lot as we talk about probability. That's not in any way a statement that I'm approving of it or that I'm encouraging it. But nonetheless, you need to know what a deck of cards has in it. So we have 4 different suits, and there is going to be then a total of how many cards in the deck? 52, 13 in each suit. And you have the hearts, you have the clubs, you have the spades, and you have the diamonds. And we have 4 aces out of that. So you get asked questions like this. You draw a card at random. Now, what does that mean? Well, you shuffle the deck a lot. And then you sort of fan it out, and I'm not good at this, but you fan out the deck, and then you just say, okay, pick a card. And magicians do this, and then they ask you to put in your mind what the card is. You put it back in the deck, and the magician magically pulls out the card you had in your mind. Okay. There are 4 aces out of 52. So what's the probability of getting an ace in the first draw? 4 out of 52. It reduces to 1/13, but nonetheless, you can go ahead and write it in its original form. Now, you have a choice, putting the card in the deck again or keeping it out. So what's your probability of getting an ace in the second card? And that's not so easy to do, because you have to consider two possibilities. That you got the ace in the first, or you didn't. If the ace was drawn in the first, you're down to 3 out of 51. If you keep the card out. If you didn't get the ace in the first, then there are 4 still in the deck out of 51. Well, how would you illustrate that? Well, if I go to the board and look at a Venn diagram, I get nothing. If I go to a tree diagram, I have something I can do. So the tree diagram. And this is like the coin, head, tails. So I'm just going to come through with some diagram of this form. Now I'm creating something very close to 90 degrees here. But I could say an ace and not an ace with a bar over the A, meaning not an ace. And so what probability do I give here? The 4 out of 52. And what is going to be true here? It was not perhaps as obvious as I'd like when you looked at what I had in the study guide. It's going to be 1 minus this for this branch. The probabilities in the branches add up to 1. So there are 48 not aces out of the 52. So this is the complement rule. The probability of not an ace is 1 minus the probability of an ace. So I'm just saying that these two add up to 1. Now my next draw, again, depending on how you want to draw your diagram and how much spread you want on these, this is an ace, not an ace. And again, remember, this is based on what? Drawing without replacement. And what I want you to realize that now the probabilities change. So what is your probability of an ace given you did not get an ace on the first draw? Notice that phrase. Given you did not get an ace in the first draw. How many aces are still left? 4, but how many cards are left since you did not replace? 51. Well, this has to be 1 minus that, so this becomes 47 out of 51. Agreed? Okay, let's go to the top branch. Okay, I'm trying to see if I've trying to keep these somewhat parallel. And I did this down here, so I'm a little bit constrained up here because I didn't plan ahead as well as I should. I'd like to have kept this so we had a vertical lineup. Okay, the assumption is you get an ace here, correct? Now, what's the probability of an ace on your next draw, given you got that ace in the first draw? There's 3 aces left out of the 51 cards, which fortunately reduces in this case, but I'm going to leave it as 3 over 51 because I want to do what? Subtract 3 over 51 from 1, getting 48 over 51, so that the sum of the probabilities in each branch is 1. Now, the argument here is that if I want an ace and an ace, so what's your probability of getting an ace and an ace? Drawing without replacement. Well, it's an ace and an ace is this particular outcome. And I mentioned to you the probability of that is simply multiply, and you want to just tweak it just a bit. I don't leave much space, but I guess that's about it, huh? The probability of this is going to be the product, which is going to be 4 over 52 times 3 over 51. Okay? Now what about the next, an ace in the first, not an ace on the second? Now I wrote AA. I could have written A and not A, an ace and not an ace, in that order. Then this is going to be what probability? Your 4 over 52 again, multiplied by what? The 48 over 51. Getting the idea? Now that's a generalization of what we're seeing on page 411. But there's a very big difference. Let's go back to the document cam. On 411, these probabilities did not change as you went to what? The next toss of a coin. But when I go to the board, the next drawing of a card, the probabilities will change because I did not replace the card. But I'm doing the same process. Now there's another wrinkle here that I need to introduce as we look at this tree diagram, and that's the idea of independence. Coming back to the document cam, the head in the first toss versus the head in the second toss, those are independent trials. So I'm going to contrast independent trials, a trial is just a repetition, versus dependent. Now, if I consider drawing a card a trial, just like I considered tossing a coin a trial, then in this case, I have dependency. Because what happened in the first draw influences the probability in your second draw. So this is considered dependent here, and when we looked at the coins, that was independent. Now that creates a very important contrast for us that we'll have to look at in extending our rules. A reminder that when I looked at the probability of A union B, we argued that that was the probability of A plus the probability of B, but it required what condition? Again, it's what Sean said earlier. A and B are what? Disjoint. They share nothing. Their intersection is the empty set. Now, in the same way, I can talk about the probability of A intersect B, or, writing it this way, as predicate logic, whereas this could have been A or B, making sure that you understand those are switchable, if you will, interchangeable. We're going to argue that this probability is the product of the two probabilities, but again with a restriction. And the restriction is going to be that the events are independent. Now, in terms of the tree diagram, it's saying that when I take the second branch, it's not dependent on the first branch outcome. So flipping a coin, those are independent trials, so this works. Now, notationally, I have to introduce some notation up here. I said the probability you got an ace in the second draw, given you got an ace in what? The first draw. That's what was involved here. So when I looked at this probability of ace and ace, I could have been a little better at writing that and could have said the probability of an ace on the second draw given an ace on the first draw. When I argued that this was 3 over 51 instead of just saying the probability of ace 2. Otherwise, this is saying that the probability of that second ace is dependent upon what happened in the first draw. So we say dependence, and so this vertical line is going to be interpreted as given. Now, if I ask for the same thing about the coin, what's the probability of heads on the second toss, given you got heads in the first toss? So if I look at this same problem, probability of heads in the second toss, given heads in the first toss, it is what? Just the probability of heads without any other information. Otherwise, knowing that you got heads in the first toss didn't change anything. In general, if I look at an event, if I talk about the probability of E given F still being just the probability of E, then the argument is that they are independent. Okay. Now, I need to add one more part in here to tie some of this together a little bit better. Okay, which camera are you on, Jennifer? Okay, would you bring number 1 back to my tree diagram on the left side, please? It'll be a while before I go back center. Okay, we're going to come to the tree diagram. Now, as I look at this, I sort of put pieces together. I said A and A not, or not A. But what if I just ask, what's the probability that you get on the second draw an ace? Okay, that I want an ace in the second draw. Well, 2 branches are involved, correct? This gets an ace in the second draw. This gets an ace in the second draw. So in that sense, I'm saying the probability of an ace in the second draw means that you have these 2 products added together. That's how you get your ace on your second draw. You can either get an ace in the first and an ace in the second, or not get an ace in the first and an ace in the second. So if I come back now to the camera here and I want to look just at the probability of ace in the second draw, I could ask for the probability of an ace on the second draw, and that's equal to the sum of 2 probabilities that are, in an essence, mutually exclusive. So they're disjoint events, if you will. That's the probability of an ace on the first, followed by an ace of the second, added to the probability of not getting an ace on the first and an ace on the second. So from a logic point of view, the tree diagram helps you get to here. So with that in mind, I'm going to have then a 4 over 52 times a 3 over 51 plus a 48 over 52 times a 4 over 51. Now note, I did something, okay, we're okay there. I thought I'd done something arithmetically incorrect. Now we have a common denominator, correct? 52 over 51. So I can go ahead and say this now is 4 times 3 plus 48, factoring out the common 4. You see that in the numerators? Okay. And so does this appeal to you in a certain way?
Yes, it does.
51 here and the 51 here, I can cancel. I'm at 4 over 52. Okay. So the probability of an ace in the second draw is 4 over 52. Yes, it is. It's the same as the probability of an ace in the first draw, which is interesting, just it's counterintuitive. Now, but that's not the point. The point I want to make here is what was the probability of an ace in the second draw given an ace in the first draw? Well, as we slide over, the probability of an ace in the second draw given an ace in the first draw was what? 3 out of 51. So my question, have I satisfied this condition here? The condition again, the probability of E given F must be the probability of E to say these are independent. So at this point, I'm saying the probability of A sub 2, given A sub 1. Let's do 2 cameras right here, flipping back and forth. I won't be back over there. This is where we need about 3 cameras so Jennifer could really go nuts. And if you're ever back in that console she's doing, it's amazing that you keep straight where you're headed. Okay, this is what I'm looking at. If they 2 events were independent, this should be equal to the probability of A sub 2, correct? But as I look over here with the other camera, the probability of A sub 2 was 4 over 52. So as I go back to the other camera, this is like the optometrist. Lens 1, lens 2. Never had your eyes checked? This is 3 over 51. This is 4 over 52. Are those equal? No. So is getting an ace in the first and getting an ace in the second an independent situation? No. By what criterion? By the criterion that if you have this condition, E and F are independent. So we are going to say if and only if E and F are independent events. That's our criterion. And that's going to be an important statement for us. Okay, so E and F independent if this condition holds. Now let's go back to the document cam. I could play the same game here and illustrate for you, and I don't think I want to do it with those three, and you come back center on the other camera here in a minute. Since you had no sleep tonight, Jennifer, this is probably pushing you beyond where I should. Let's come back to the tree diagram in 4.9. You could argue now, by what we've done, that if you look at this diagram, which is what I have on the board, okay, you could argue independence of the two events and contrast that to these two events here on this diagram with a coin, in which now I would ask, what's your probability of heads on the second toss? Well, it's these two branches. And so that would be 1/4 plus 1/4, which would be 1/2. What is the probability of heads in the second toss given heads in the first toss? Back over here. Probability of heads second toss given heads first toss. These are coins. Do they have memory? This is just 1/2. Getting ahead on the second toss is still 1/2, no matter what happened in the first toss. And we said if we just add the probabilities in those two branches, which means I'm interested in just the probability of heads in the second toss, which is the probability of a head on the second given a head on the first, plus the probability of heads on the second given not heads on the first. Those are the two chances you have, correct? This is one. Okay, just a moment. Got to stop and think what I want here. Didn't say that right. Ouch. I should have said and. Let me modify that. I jumped ahead notationally. Okay. Need some space here, and I need to clean that up a little bit. Heads second and heads first. Heads second and not heads first. Those were the two branches. Now, if I look at that and look at what's on the document cam, remember you're going to multiply these in the branches. This comes out 1/2 times 1/2 plus 1/2 times 1/2, which is 1/4 plus 1/4, which is 1/2, and these two are the same. That needs to be tweaked just down a little bit. But the argument of independence is predicated on, again, the statement that these two probabilities are equal if and only if E and F are independent. Now that's what Chapter 12 is about. We call this conditional probability. And the tree diagram is very important to this concept. Now I'm going to go back center. Are you ready for that? Okay. So as I come back to center, I'd like to look at what else is in this presentation in Chapter 4. Just in passing, 413 is the presentation we did in the Yahtzee problem. 413. Now that's important to you to the extent that yesterday I talked about the Yahtzee problem with tetrahedral dice, and I'd be sitting there trying to do that problem for myself with tetrahedral dice to make sure that I understand the probabilities involved going through the back door. The complement rule is discussed here on page 415. It is hot spot number 3. And again, illustrating the notes of what we did in terms of the Yahtzee problem. Just related to that, so I don't overlook it, this becomes an extremely important part of what we're doing with probability. I'd like to look at this statement and tossing coins. Now, in this particular case, I believe we are talking about 3 coins being tossed. The phrase, the probability of at least one tail, means 1 minus the probability of no tails. And that is a problem that is going to be very important to us. We'll come back to it, but that's in 415, and you'll need to read about that. But on page 417, this is the material that is very much related to what I've done on the board today, independent events versus dependent events. And I do this in terms of dice rather than drawing cards. So there are several examples carried through here that I think you will find helpful as you try to deal with dependent and independent events. There are sample problems, and then there is a general formula that I've just talked about. This is on page 421, and the notation I just introduced, okay, is going to allow us to look at general formulas as we go down 421. I'm going to slide down. Here's your general addition rule. It's going to be part of chapter 12. And here's the one I've been working on this morning. The probability of A and B is the probability of A times the probability of B given A. And there's an equivalent form at the bottom as we go down to the last part there. That's what I've been spending time on today. There's 21 pages so far that hopefully will help as we come off there. And then we actually generate out of that on hotspot number 8, page 425, a general formula that's going to be very critical to us as we spend time in chapter 12, the probability of B given A as a quotient that you're looking at right here. This will be an extremely important formula for us on page 425. And then, as we go from there, there are a variety of chapter test problems. There are 10 of them on page 428. And so you have 30 pages related to probability, and they are some of the most important pages of the entire presentation of probability, because David Moore very much cuts some corners trying to avoid some language, avoid some notation that's going to be very much a part of what we do. So the general rules that are talked about in the study guide are covered on page 307 in your text. Here is that general rule for the addition rule, where we subtract off the intersection of A and B probability. So what you're looking at here at the bottom of the page, where you have minus the probability of A and B. Okay, and you've looked at a tree diagram. You have a better idea what that means. It's the intersection of A and B from the Venn diagram. And then coming off there, that was page 307. Then we have a general multiplication rule that's covered on page 311. This should help you understand a little bit better with this notation. The probability of A and B equals the probability of A times the probability of B given A, and you see the phrase conditional probability on the monitor as you look at what I have shown there. That's my effort to focus you on a particular phrase. So this concept, as we go to the board, as I go to camera 2, up here, and what it means to have the probability of E given F, if you have independence, then this allows you to take this idea and slide over. We'll just pan over here to the left, in which I have this multiplication rule in its very simplistic form. The multiplication of the two probabilities, but it assumes independence. That's the caveat. The probability of A or B assumed that there was no intersection between those two events. These are the two simple rules. Now, how do you avoid getting caught in this kind of, is it independent or not? And as we slide over and pan further, the key to much of this, to avoid some of the problems with logic, is a what? Tree diagram. Okay? Now, from the standpoint of the course, as I come back center on this now, in terms of the course, traditionally, I told you that probability was a part of the introductory course. And there are two different branches that we can pursue coming off the introductory chapter 10. One has to do with the ace, not an ace example I have on the board, conditional probability. And we're going to, next week I suspect, I'm going to delay it until then, we're going to talk about drug testing. Because whether it's drug testing in terms of substance abuse that becomes a critical issue in things like the Tour de France, the Olympics, running in general, the medals that have been taken away because of blood doping, which isn't a drug abuse per se, it's just trying to introduce more oxygen into the blood, or taking something that isn't considered a drug in the same sense that heroin might, but if you take something that has, for example, caffeine in it or testosterone, that in some way it's going to enhance your ability. We do a lot of that testing, and we basically remove medals. We say you didn't really win when we thought you did, or we fire you from a job. You need to understand that there's a false positive involved, potentially. We say that you did the drug and you didn't. So we come out a positive, and that says, on the basis of that, I should strip the medal. Well, the question, what's the probability that you get a positive given you did not take the drug? Now, I can take it out of drug abuse, and we just say a cancer test. Your cancer test comes out positive. What's the probability that you have a positive cancer test given you do not have cancer? That is something we can do with the tree diagram using conditional probability. And that's what we will do. We'll look at HIV testing. And the big issue right now in Africa with these massive infection rates is to go into a village, do a test, and give you the results in the same day. Any testing we do here goes to a lab, and you're lucky to find out in what? A week sometimes, and you sit there not knowing. Well, if you go ahead and go into a village where people aren't going to be available a week from now, otherwise they come from surrounding villages, you give tests, you want something while they're waiting. Well, that is where we're going to look at. Now, the other branch, besides this thing called conditional probability, and I'll just throw another word in here before I forget, it's referred to as Bayesian statistics, named after Bayes, B-A-Y-E-S. We'll come back to that as part of this question about testing for diseases or testing for drug abuse or substance abuse. That will be referred to as Bayesian statistics. Now, the other branch we can follow is related to what I showed in the study guide where you toss 3 coins. Remember I asked, what's the probability that you have at least one head? Well, if I'm tossing 3 coins, I can keep track of the number of heads I get. So I can define a probability distribution where X is the number of heads I get in the toss of 3 coins. So I could have X as high as 3 and as low as what? 0. I could get 3 tails. So X being the number of heads, 3, 2, 1, and 0 are my possible values. What are my probabilities for each of those values of X? Okay, now that you could find just by looking at what we did a moment ago. Let me bring that back under the document cam, where we had the 3 heads. This is on page 411. That problem is answered just by looking at this diagram. On page 411, And I have only one branch with what? 3 heads. So the probability that x equals 3 is what? 1/8. Now let's look at 2 heads. How many ways can I get 2 heads looking at that diagram? Tell me, how many branches have exactly 2 heads? If you don't have the book, you can look at the screen. How many? Do we agree that there are 3 branches with exactly 2 heads? Here is one right here. Here's another one. And we don't hit the next one until we come down to what? Right here. But each of those 3 has what probability? 1/8. They are mutually exclusive, so we just are going to add the probabilities. So what's the probability that x equals 2? 3/8. Now, I could play the same game with 1 head and get 3/8. And the probability of 0 heads, as we come back to the diagram, it's the last row. Tail, 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 1/8 probability. So you have generated a probability model for tossing 3 coins and counting the number of heads. Make sense? So I could have no space up here, but I'm going to try, just for the moment, going to right here and just see if I can fill in a small little diagram in the space I have. I'm not sure what I want to do with the other board yet. So I could make a very simple table, as long as I can draw that tree diagram. And we said 3, 2, 1, and 0, and you just agreed, I hope, that these probabilities came out of that. So I have a probability model for tossing 3 coins. Trevi Fountain problem. Okay. Now that is a very interesting model, because you can get those same answers by taking p plus q as a binomial to the 3rd power. So again, I can take p plus q, a binomial in parentheses, take it to the 3rd power. I don't know how well you remember your algebra. That's p to the 3rd plus 3p to the 2nd q to the 1st plus 3p to the 1st q to the 2nd plus 1 q to the 3rd. It's called a binomial expansion, because that same expansion with p at 1/2, q at 1/2 gives this model. We refer to this as the binomial probability distribution. And so we have a whole chapter on that particular discrete probability distribution. So with what we've started here, we go into 2 different directions. A binomial model, there's a whole chapter on it, and the Bayesian statistics, where we try to find the probability of a false positive, because it's such a part of our culture right now. Each of those is a chapter in its own right. And that's what I have to try to put together in these couple of weeks that we spend on probability. Now, relative to what we're doing here, so far I have isolated only on Chapter 10. You should be able to now spend time in Chapter 10 for the homework over the weekend, and on Monday, my expectation is that you can come back to Chapter 10 and have it done. The material on the binomial distribution, at best, is next week, if not beyond that. And so I'm going to come back to where our schedule is, looking at the computer here in a moment. I've had it on this time. So I'm going to come back to the computer, which isn't quite center. I have to tell Jennifer where I'm disappearing to so she knows where to predict I'm going to be with good probability. So as I come over here and I click the laptop and I click another button and play the magic of technology that sometimes works, I'm going to scroll down, if I can clear the physical desktop so I can reach a mouse, and scroll down here a little bit, if I can get to the bottom. Okay, and bring this up. Let's see what I want to do here. Give me a moment, Jennifer. Okay, I'm at week 8, and we are at what week? There we go. We are at week 6, correct? Okay. And week 7 is coming up. So, by the way, that week 7 is a rather important time because what does that represent, roughly? The median of the semester. Jennifer's celebrating, but she's the only one. Halfway through the semester, and so that gives you a sense of why maybe you're tired. But I'm going to scroll over just a little bit to the right for the 6th week, and you'll note the only thing that's true there is Lab 7. Because Chapter 8 we did already. That was on the difference between random sampling and systematic sampling, and we covered that in essence as we talked about how to get a random sample in Lab 7. Chapter 11 I have mentioned to you, as we've covered that this week, Monday. We talked about Lab 7 and the sampling distribution of X bar. We've done, for all intents and purpose, we've done Chapter 11. And so what I'm trying to do before I hit the homework there, I decided to go ahead and hit Chapter 10. Now what you'll note here, that next week, Chapter 10 and 13 are involved. 10 is the introductory chapter on probability. 13 is the binomial distribution, and there's nothing said about 12. So what I have done this week so far is look at 10, 11, and 12. I'm reserving 13 for next week, assuming that I can cover 12 and 13 combined next week. So the question, where does that leave us in Chapter 11 in the text? Part of the homework I want you to do this weekend is a reading assignment. I want you to read Chapter 11. And I think you're going to find that as you read Chapter 11, we basically have done it. The only thing I have not put in a kind of formal presentation is calculating a Z. Now, in answering Erlinda's question Monday about whether or not her X bar was unusual, I asked how many standard deviations from the mean was her X bar. But remember, I had to take sigma over the square root of n to do that. Well, I could have done a z-score, where I would have written the following formula. And let's see, I might be better getting it in the book than I am trying to write that on the board. But in Chapter 11, there is a formula that I simply want to present to you. And this is under the central limit theorem. And I'm hoping that David Moore presents it in a nice, formal way. And I'm not seeing squat there, so I'll say it. X bar minus mu over sigma divided by the square root of n. That's your new Z formula. X bar minus mu over the denominator, sigma over the square root of n. If you use that formula and read what's done in the text, you should be able to answer Erlinda's question, how unusual was her X bar, that we answered on Monday. So that's where we're headed. Tomorrow, I'm going to spend more time in the chapters. I'm going to try to put more pieces together for you. We are going to possibly be able to look at the test results and talk about the test that you took. So that's sort of up in the air depending on how the grading goes that I'm trying to finish up today and tonight. So as we go back to Jim Morrison and the Doors, what is your choice as we close down, Jennifer?
Button.
The bad part of the end is 45 seconds of silence at the beginning. So you better fast forward right now to a large part of that, or we're going to have a lot of silence as we close down here in the seconds I don't have. Have a pleasant morning as we go to the slide.